Hi guys, welcome to our second video in chapter 19. This video is going to cover section 19.2 and is all about the strengths of acids and bases. So you can see on the right, we've got our list of objectives. We want to be able to relate the strength of an acid to its ionization constant or its degree of ionization. We want to compare the strength of a weak acid with the strength of its conjugate base, and the same with a weak base with its conjugate acid. And we want to be able to explain the relationships between the strengths of acids and bases and the values of their ionization constants, okay? And you can see our list of vocab we're going to learn here, okay? But let's start by talking about the strengths of acids, like how strong is an acid? You know, we all know sulfuric acid is pretty strong, and we all know acetic acid, otherwise known as vinegar, not quite as strong, okay? So let's take a look at some of this. So first thing I want us to remember is that acids can conduct electricity. That was one of the properties of acids we talked about in the last video, except not all acids conduct equally. And in fact, studies and experiments have been done. And when we put 0.1 molar hydrochloric acid into a container and we test its conductivity and we compare it to the conductivity of 0.1 molar HC2H3O2, otherwise known as acetic acid, that's vinegar, right? We find that HCl conducts far better. And you can see that the light bulb is all the way lit up here, where it's not all the way lit up for our vinegar. So that tells us that those two substances, the hydrochloric acid and the vinegar, they're not producing the same amount of ions in solution. And so one acid must be producing more ions. Hydrochloric acid, in fact, is producing more ions, right? And we said, therefore, some acids must ionize better than others. Well, the result is that some acids, which can completely ionize, are called strong acids, right? Again, acids that can completely ionize are called strong acids. And HCl is a strong acid. If we put 0.1 molar hydrochloric acid in the solution, then we will have 0.1 molar hydrogen and 0.1 molar chloride, right? They will completely separate. Weak acids are acids that only ionize partially in dilute aqueous solution. Okay, so let's compare those. I have two pictures, right? If we look at our HCl, you can see that in our solution, our atomic picture of the molecules, there is no HCl molecule. In fact, there are only chloride ions and there are hydronium ions, which have accepted the hydrogen from that chlorine. Okay. And then if we compare that to our vinegar, here we can see that we actually do have some complete acetic acid molecules. Some of them are complete. Some of them have disassociated to form this acetate molecule. And that hydrogen has gone on to a water to form a hydronium. So it's a little more complex than our strong acid, though, because we do still have our reactant at equilibrium with a weak acid. We still have some of that acetic acid molecule. Okay. All right, so let's get into it. Let's start talking about how we can classify this. First question I have is, can the Bronsted-Lowry model explain why HCl ionizes completely but acetic acid doesn't? Right? We could talk about strength of ionic interactions and all that fun stuff. But when we're talking about the Bronsted-Lowry model, we want to actually include the concept of its conjugate base, of the conjugate base of this acid. So what we've said is, because in this example, HX is a strong acid, that means that its conjugate base must be weak. So because that the conjugate acid is fairly weak, because of the conjugate base is very weak and unable to get rid of that negative charge. It's unable to go backwards in this reaction. It favors the forward reaction at equilibrium. Okay, so it favors that forward reaction, and so our HX will nearly completely dissociate into its conjugate base X minus, and it won't be able to attract that hydrogen back. Okay. Again, that's very strong acid. Well, let's look at if it's a weak acid, right? It says if HY now, we've changed this from HX to HY. If HY is a weak acid, the ionization equilibrium lies far to the left because the conjugate base Y minus has a greater attraction for the hydrogen ion than does the base H2O. So in this case, our acid is fairly weak, which actually means that our conjugate base is fairly strong. So this favors the reverse reaction. This conjugate base is strong enough to pull this hydrogen off of the hydronium and back onto this conjugate base, reforming the acid. Okay, so it's strong enough to pull that back. So that's a strong acid and a strong base, or sorry, strong acid and a weak acid in terms of Bronsted-Lowry. Also, by the way, this explains strong acid and weak acids in terms of behavior, but it doesn't yet provide a way to express this mathematically. We can't compare the strengths of acid. We could just say HX is stronger than HY, but we have no idea. Is it as strong as sulfuric acid or nitric acid, or is it like vinegar? Like, we don't really know yet, okay? Which brings me to our acid ionization constants. Okay, and this is where we put math on this thing. So it says the acid ionization constant is our value of the equilibrium constant expression for the ionization of a weak acid. Notice this is only for weak acids. This is not for strong acids, which aren't really at equilibrium. They're just fully dissociated. Okay, but for weak acids, okay. So in this example that I snipped out here, we have our HCN, our hydrocyanic acid, combining with water in an equilibrium with hydronium and cyanate, okay? So our regular, if we were to do this 2 units ago and I said calculate the equilibrium expression, you would do so by taking the concentration of your reactants, dividing it by the concentration of your products, raising them all to their coefficients, which in this case are all just ones, okay? So this would be our equilibrium expression, except we're not really dealing with an equilibrium expression. We're dealing with our acid ionization constant. So we're going to simplify a little bit. It says the concentration of liquid water in the denominator of the expression is considered to be constant in dilute aqueous solutions. So that means we can pull it out, combine it with our KEQ, right? That's like we've pulled out that H2O, multiplied it by KEQ, and we've arrived at something called a Ka, which is our acid ionization constant, right? We got rid of the H2O because its concentration doesn't change. So our acid equilibrium constant, our Ka, is equal to our hydronium concentration times our cyanate concentration divided by our hydrocyanic acid concentration. Notice Ka is very low. That tells us that this is a weak acid because it means that we have more reactants than products. And in fact, the lower the Ka, the weaker the acid, okay? It says right here, the 3 asterisks, right? The weakest acids have the smallest Ka values because their solutions have the lowest concentrations of ions and the highest concentrations of unionized acid molecules. I actually have on the right-hand side here a table of some acids. Notice hydrosulfuric is different than sulfuric. And I'm showing you the Kas. And notice for hydrosulfuric, we lose our first hydrogen, and the Ka is pretty small at 8.9 times 10 to the negative 8. But then when we try to remove that second hydrogen to form just S2 minus and H plus, it goes all the way down to 1 times 10 to the negative 19. So it's very, very, very weak acid. That second hydrogen is very hard to get it to come off. And you can read down here. We have lots of acids here that we can see. Okay. Let's talk about strength of base. Strengths of bases, right? It's really very similar to acids, except when we're dealing with bases, we're dealing with hydroxide rather than H plus. And in fact, whenever you are dealing with bases, you can consider them to be mathematically identical to acids, except we're talking about hydroxide rather than H plus. Okay. All right. So strong bases are bases that dissociate entirely into metal ions and hydroxide ions, right? So again, that full dissociation. Whereas our weak bases only partially ionize in dilute solution to form our conjugate acid of the base and a hydroxide ion. So again, we're making a hydroxide ion here, and that's our conjugate base to our acid, which in this example is water. Because remember, water can be both an acid and a base. And likewise, our base here is going to form its conjugate acid after it loses that proton, okay? Sorry, after it gains that proton, the base is going to absorb a proton. That's what makes it basic. It's stealing a hydrogen from this acid. Okay. All right. You can see I have here some common strong bases you can read through, but they are all metal bound to a hydroxide. Also notice that we have things like barium hydroxide that have 2 hydroxides, and we have things like sodium hydroxide, which have 1 hydroxide group. So important to know, not everything has the same amount of hydroxide ions in it. And so just like we had the ionization constant, which was Ka, The base ionization constant for an equilibrium, for a base at equilibrium is the Kb. And again, it is our unreacted base, our reactants in the denominator, and our products, our ions in the numerator. Okay. And again, I have some weak bases and I have their KBs over here, their base ionization constants, along with their equilibrium expression. Okay, so you guys can take a look at those if you'd like. Now, a couple of things I would like to make sure that I hit on before ending the video here. Strong is not the same as concentrated, and weak is not the same as dilute. Strong versus weak refers to how much the substance ionizes, where a strong acid or a strong base will fully ionize. Dilute versus concentrated refers to how much is in a volume. So you can have concentrated acetic acid. It's very vinegary. It smells really strongly. It's just not that strong though. It's not anywhere near as strong as even a dilute sulfuric acid. Okay, but it's just how much is in a specific volume. All right, guys, that's all I have for this video. Thank you for listening. I will see you in the next one.